Swayam Prabha. Digital India. Educated India.
Okay, good morning. Today we will talk about another kind of distillation practice called batch distillation. It can also be called simple distillation. And another name is differential distillation. So all these three names mean the same. So before we look at what this batch distillation mean, let's recollect what flash distillation was all about. So in the flash distillation, what we try to do is, if we have to show from a PXY diagram, so this is a PXY diagram. This corresponds to vapor pressure A, this is corresponding to vapor pressure B, this is bubble point curve, and this is a dew curve. So the idea here is you take a liquid and then you decrease the pressure and then reach a two-phase region. Okay, the moment you bring it here, the phases will phase separate corresponding to the compositions on the bubble point and on the dew point. So the liquid will be having a composition corresponding to this bubble point, and the vapor will have a composition corresponding to this dew point. Once this phase separation is complete, you physically separate this mixture and take it away. That's all, one stage. Okay, so this is flash distillation. This is something that important that we have to remember this particular operation because it has a bearing in how we are going to discuss about batch distillation. In the batch distillation, we will do a similar operation, but instead of doing in one shot flash, we will do many number of flash operations. Okay, at each of those flash operation, we will create very small amount of vapor. So here we are making a significant amount of vapor in liquid and separating it. In the simple distillation or batch distillation, we are going to do the infinitely large number of flash operations. At each of these flash operation, we will create only a very limited amount of vapor. So what that means in terms of this PXY diagram or TXY diagram. So this is for flash. When we do this batch or simple distillation, let's say I have this time I will take TXY. Because in the batch or simple distillation, temperature is the control variable. We change the temperature to vaporize and condense, whereas in the flash we work with the pressure. Okay, so this one corresponds to TB, boiling point of temperature, boiling point of species B. This is the boiling point of A. So here the liquid starts here and you kind of heat it, you will reach the bubble point. Okay, so this is bubble point curve here and this is a dew point curve. So we start with a binary liquid mixture, we are heating it and then we will reach the bubble point. At this point, a first bubble will form, which will have a composition in the vapor phase corresponding to this dew point curve. Okay. Now imagine the moment this first bubble forms, let's say I am taking it away, I am just removing it from the system. Okay. So in the flash, they were in equilibrium. Once the equilibrium is reached, we separate them. So here, the first bubble that forms from this liquid is taken away from it. Okay, the system is gone, it's taken away and then condensed and then taken away from the system. So what do you think would happen to the composition of the liquid? Will this remain here? So you have to picture this in your mind. So you got a liquid mixture, you are heating it to a bubble point, a very small amount of vapor forms corresponding to this composition. but that vapor is taken away from the system, it's gone. Now with respect to liquid, now the system is only the liquid at this particular temperature. What would it be? What would be its composition? Would it be same? So remember, it would be same if the vapor also had the same composition as the liquid, right? If the liquid and the vapor, if they both have the same composition, let's say, which corresponds to an azeotropic mixture, then when I take small amount of vapor out of the system, the liquid will still have the same composition. But we know that these are not azeotropic mixture. Here we are talking about a mixture A plus B, where A is more volatile, meaning whenever I create a small amount of vapor, the vapor would be richer in A compared to the liquid. What that means is the liquid phase composition would have become little lesser than what it was at the bubble point. Okay, so I may think something like maybe here, since it is a pure liquid now and the composition is smaller in X because more amount of A has gone into the vapor, so we are talking about this point. Now you see this point is below the bubble curve. That means this new point after the first flash, the composition of the liquid will correspond to somewhere here. You see that it is moving to the left because the composition of the composition of A is decreasing because more and more A is going to the vapor, but still it is below the bubble point curve. So what we need to do, we have to have more heat. We add more heat at this point so that we reach this point. Okay, so we are adding little extra heat, and then what happens is we are reaching a new bubble point. At this point, we will establish another vapor formation because of flash. Let's say here also I am taking this vapor away and I am mixing with the vapor that came before. So I am collecting it. I am taking this vapor, putting in the container. The next fraction, when it comes here, I am collecting that vapor, condensing it and putting it back into the reservoir. Now with respect to the still, with respect to the distillation column that I am talking about, in that the composition would be now lesser than this point, because some amount of vapor has been removed, some amount of A is taken out. Okay, so it moves somewhere here. At this point again I am below the bubble point, and I have to supply heat and then increase this temperature to bubble point temperature here, and again I have another set of flash, right? So I can keep on doing multiple times. So here I have shown a discrete set of points, but actually how it happens is it is happening in a differential manner, so that a very little or infinitesimally small amount of vapor is created and taken away. Okay, so that means you could actually go along this curve. This is very different from flash. In flash we go right into the two phase region and wait for the two phase separate in one single stage. But in the simple or differential distillation, as soon as the vapor is created, the vapor, whenever the vapor forms, it is at equilibrium because this corresponds to bubble point. But the moment the vapor forms, we are going to separate it, condense it and then take it away. Then work with the remaining liquid. The remaining liquid would have a lesser composition in A and would be at a temperature away from the bubble point. So again you apply heat, you supply heat, again bring it back to the bubble point, create new vapor, collect the new vapor and then put it together with the previous vapors, and then again you do subsequently successive number of flash operations, and this is why it is called differential distillation. Now if you think about the vapor, the first vapor that you created would have a highest value of Y, right? This is the first dew that you happen to have will have a highest value of Y. The next cut had a smaller Y, right? Remember this X and Y both are actually read from the X axis. So this Y is the highest possible you can get in the first flash. The second flash gives you slightly lesser mole fraction. When you mix all these things together, you will get an average quantity. Okay, so whenever you collect the vapor, condense it and put it together, when you sum up all this composite vapor, that would have an average composition over a range of compositions. Okay, it is not a single vapor composition like in flash. Here is going to be an averaged composition of the vapor. Okay, whereas the wherever you stop the batch distillation, and the composition of the liquid will correspond to the bubble point. Okay, so it's very important to note that what we are trying to do here is, in the differential distillation, we are actually doing a series of infinitely large number of flash operations, and in each flash operations we are removing the vapor and taking it away from the system, okay. And then the liquid will have to undergo many heating vaporization cycles, okay. As far as the liquid is concerned, it will be always near the bubble point curve, whereas a vapor would have an averaged composition over a range of compositions, okay. So these are important points. So this is what the batch distillation is all about. So now what I'll do is I'll show a schematic of this instrument or the apparatus that we use for simple distillation. This is very important because this is something that you will do an experiment in your master and sir lab, maybe this semester or next semester, okay. And we will set up a mathematical model to characterize this process, whatever you have just stated here. Which one? The liquid. Like I said, so basically, like I said, there will be a small dip. There is a small change in the concentration, right? The composition, right? So that's why it actually goes a little bit away from the bubble point, but then you're constantly applying heat. Yeah. So if it's an azeotropic mixture, the two curves will be the same curve, right? The two loops will actually converge into a same line. Okay. So then when you vaporize, the vapor and the liquid, they have the same composition, right? So no matter how much vapor you take it away, the liquid will have always the same composition. Okay. But here that's not the case. Here when you vaporize, the vapor contains more of A than in liquid. Okay. So Y is more than X. Okay. Because of that, what happens is, let's say you start with 100 moles. Okay. And let's say that initially you start with 0.5 mole fraction. So it basically means that you have got 50 moles of A and 50 moles of B in the feed. Okay. So let's say you are actually vaporizing some 2 moles. Let's say in the 2 moles also the mole fraction is 0.5. If that's the case, then the liquid will have still the 0.5 mole fraction, right? Because the liquid will have 98 moles, still the composition will be 0.5 and 0.5. Vapor will have 2 moles of vapor with the 0.5. This is corresponding to azeotropic kind of a mixture. Now let's say when you vaporize 2 moles, you see that 90% is A and 10% is B. Okay. So that means in the vapor, out of 2 moles, 1.8 moles are A. Okay. The remaining 0.2 moles is B. Now when you come to this liquid phase, the total moles will be 98, but the composition would have been now different because more A has gone to the vapor phase. So there are some saying that the liquid will have a slightly lesser composition in A once the vapor is removed. If the vapor and the liquid are kept together, the average composition will remain the same because the system now comprises both liquid and the vapor. But here I am taking the vapor out of the system. So vapor is not my system anymore. So here my system is only the remaining liquid. Now I am asking, in the remaining liquid, is the composition same or keep changing? You will see it will keep changing. It will actually go to smaller and smaller values in this case. Yes, it is because of the relative volatility. Yes. So there what we do, we don't just do this operation at the bubble point, we go well inside this two region loop, right? That's what I was trying to say here. We don't stop here or we don't stop here, we come well into the middle of this curve somewhere and then we let it phase separate in one shot. So here on the other hand, we come here and then we collect the vapor and remove it, supply more heat, move to this point, vaporize it, collect the vapor again. So it's a series of operations that we do. Okay, so let's look at the apparatus that is used for this batch distillation. So typically you'll have a vessel, and this will be a jacketed vessel so that you can send steam in and steam out to provide heat. Okay, so this contains this mixture, liquid mixture A plus B, and then what you have is you take this out, the vapor, and then you send it to a condenser. So condenser also will have a jacket where the cooling water will be sent in. And this vapor, once it comes out of the condenser, so this is a condenser. This would have now the liquefied condensate, and this can be collected into a receiver. It's called receivers, yeah. So you can see it's a very simple setup. It's something you can easily set up in your lab. All you need is a flask, provide a heating arrangement, and then you charge with a some amount of liquid of initial composition, and then you start heating it. Okay, so in this case, the moment the vapor forms, it will flow through this condenser, condense it, and then you can collect it here. Okay, so this is a condensate. So one more thing you can have here is I was talking about mostly a binary mixture A plus B, but you can have multi-component mixture also. Let's say you have A plus B plus C. Okay, such that the volatility of A is much more than the B, and then B is more volatile than C. Suppose if you have this case, what you could do, you could first collect for the first several minutes. Maybe you can collect in one container, and this will have rich in A. After some time, mostly all of the A must have gone. Now the next would be the B. Component B will vaporize. You can probably take it away and then put it into another receiver, and this will be rich in B, and whatever is remaining here would be rich in C. Again, we are not talking about pure component A, B, C. We are only talking about, compared to the original solution, am I able to fraction it into liquids which are rich in A, rich in B, and rich in C. Okay. So for this kind of a multi-component mixture, you can have series of receivers to make the cuts kind of collected at a different time intervals. Okay. So this is a time dependent operation. It's a batch operation, like I said before. So you can distill for some time, collect, that will be rich in A, and the moment you see that the composition A keep changing, then you can actually divert it into another one. Here you will see more B is getting collected, and then when you stop it, the residual liquid will have more in C. Okay. So in a way, you can use this for binary distillation as well as for the ternary distillation, but still this will not give us pure components. Okay. It will give you only slightly richer species in each of the cuts. So now having looked at this particular schematic, now we will set up a mathematical formulation or modeling to understand how do we operate this batch distillation. So what we'll do is we'll do a simple mass balance for the so this is called kettle or reboiler, what you want. So you can actually find the you can write the mass balance over this kettle, and then we will see that so we would like to write something like number of moles in minus number of moles out, and that is equal to accumulation. Okay, so we would like to write something like this. So now what we will do is we will say that moles in, moles out, accumulation, and then we will do this for total material, and then we will also do this for species A. So since this is a batch system, is there anything coming in? Nothing is coming in, right? So we will put 0 for both total material as well as for the species A. Moles out. So here we will say very small amount, differential amount of vapor is created, which will denote as dD. And as far as the species is concerned, so what is actually going out? So you have to think about this more like a semi-batch system. You start with the liquid mixture, and then constantly you are creating vapor. Okay, even though when I discussed, I said we are doing it in steps, but actually we are doing it continuously. Okay, so in terms of species A, anytime the vapor that is formed, it is always formed corresponding to the bubble point dew point curves. Okay, so the composition of vapor is always at equilibrium with the corresponding liquid whenever it forms. The moment it forms, it is removed. Okay, so we will say the amount of species that is removed from the system because we are collecting the vapor would be y times dd. Y is the equilibrium mole fraction of the vapor corresponding to the dew point. dd is the number of moles of vapor we created. So this dd is a total mole. Y times dd would be the total moles of A in the vapor. 1 minus y star times dd would be the corresponding B, species B. So then if you look at the liquid, okay, in the liquid there will be a accumulation equivalent to dl. So here L denotes the number of moles of the residue liquids in the kettle. In the case of the species A, we will write the change, the accumulation term is L times X and the differential component. Why we do this is because if I look at the liquid, the total moles are changing because some moles of vapor is gone, and I also said the composition will also change in the liquid. That's why I write d of Lx. Okay, if you want you can write this, you can expand this as L dx plus x dl. This is the accumulation term for species A. So now we can collect all this term and then write this mole balance. With respect to species A, so moles in is 0, moles out is y star dd, and the accumulation term is L dx plus x dl. This is one equation, and then if I have to write for total material, in is 0, out is dd, and accumulation is dl. And now I can replace dl as minus dd. So this equation will become minus y star dd is equal to L dx minus x dd. Okay, let me do this little so here I am trying to write in terms of dd, but I want to write in terms of dl. Okay, so let me write this in terms of dl. So so from here minus y star, for dd I can write as minus dl. On the right hand side I have L dx plus x dl. Okay, I want to write everything in terms of L and dl. So if I take dl out, I will have y star minus x, that is equal to L times dx. Now I can separate the variables. I have dl by L here, and I have dx by y star minus x, and this can be now integrated. Now when we do this integral, so we are looking at, our interest here is what is the amount of liquid that is present at any point of the operation. That's why I am doing in terms of L. So initially we had I think I use F. Yeah, so what I can do, I can actually integrate from W to F, and here correspondingly XW to XF. So this F here is a total mole that is present initially. W is a total amount of liquid that is present after the batch distillation is stopped. Okay, it's like initial and final amount of. So let me write this. F is the total moles at time t equal to 0, and W is the total moles of liquid actually at the end of the operation. I think we don't have to write this total because we are referring to anyway liquid. So we say moles of liquid. So in this problem anyway we started with initially a complete liquid system. So F corresponds to liquid at time t equal to 0, and XF is the mole fraction of A at time t equal to 0. XW is the mole fraction in the liquid at the end of the operation. So, this particular equation has a special name to it. Okay, actually we can integrate this out, because this will be just simply ln of f by w. On the right hand side you have this xw to xf dx by y star minus x. This equation is called a Rayleigh's equation. So, you can see this equation kind of relates. So, what we generally know is that f is known and xf is known. W and xw will depend on how long you run this operation. Okay. So, typically we are interested in, if I know the w, that means I know that I operated for certain time, then I measure how much quantity of w is present, okay, and then that corresponds to some amount of xw. Okay, and there are other questions you can ask. What would be the composition of the vapor phase, and there are many such questions you can ask. But if you want to go anything further from here, suppose you want to find this out, what you need is, you need a VLE data, right, xy data. On the right hand side you see that you have got variable x and then you got y also, and y is a function of x. So what you can hope to do is, if you know the VLE data in terms of xy data, you can write y in terms of x and then you can integrate this out. Okay, so that's one possibility. Or what you could do is, if you get an analytical expression, that's well and good. Otherwise you can actually do this numerically. Okay, so for each x you find the y star, and then you find y minus x, and then you plot 1 by y minus x, and then integrate over a range of x values. Okay, so that's how you manage these equations. So before we do that, so what I'm going to do is, I will assume that the relative volatility alpha is constant. If that is constant, I can write y as a function of x. I showed in one of the previous class during Rayleigh's using Raoult's law. We will do that, but before we go there, let us also write this equation for the composition of the vapor. Composition of the vapor can be obtained from a simple mass balance. So remember, F times xf should be equal to W times xw plus D times some y average. So what we are saying is, the total mole of A that is present in the beginning is actually now distributed into the residual liquid and the various amount of vapor that we have collected over a period of time. Okay, the liquid is existing at xw mole fraction, and W is the number of moles of liquid, and D is the total moles of vapor we have collected so far. But we are writing y average because the composition of the vapor was keep on changing. Initially it was very rich, and then as you continue the operation, the y was decreasing. So this kind of a mass balance will tell you an average vapor composition. Okay, so sometimes we ask, what is the average composition of the vapor phase after the batch distillation is over? So you apply this kind of mass balance. So now let's deal with this Rayleigh's equation and see if I can get an analytical expression for some specific cases like constant relative volatility. Okay, so we'll assume that alpha is constant. So alpha is nothing but relative volatility. I think I showed in one example between benzene and toluene, and I looked at VLE data and I calculated alpha. Alpha is nothing but Pa by Pb if you have Raoult's law following mixture, and even though Pa, Pb are functions of temperature, but the ratio can be not so much sensitive to temperature. So you can think about having an average relative volatility. Okay, so in that case, y can be written as something like alpha x by 1 plus alpha minus 1x. Okay, you can refer to this derivation involving Raoult's law in one of the previous classes. So this equation is for constant. You can actually use this expression if you can assume constant volatility. So I can actually use this to substitute here. So let's do this. So let's say I want y minus x. So this is y and then minus x. Yeah, so this is basically the final equation here. We are going to use as Rayleigh's equation for constant alpha. So the implication of constant alpha is important because you can consider that to be constant in this integral. Alpha is independent of the composition, so that comes out of the integral. So that's the advantage of assuming this to be a constant relative volatility. I think an equivalent form of writing this is, you could from here, I think what you can do, I will write this one because I think the textbook basically writes in this form. So here we have ln of f by w 1 by alpha minus 1 ln of xf 1 minus xw by xw 1 minus xf plus ln of 1 minus xw by 1 minus xf. So these are basically equivalent forms. Okay, these two are essentially the equivalent forms. So the way I am writing this one is, from here I am combining these two terms, then I get this. So here there is a minus sign, I am inverting it, so I get plus ln of the inverse of this, which is 1 minus xw by 1 minus xf. Okay, so both forms are equivalent. So this is all about batch distillation or differential distillation. There is also possibility of the opposite process called partial condensation or differential condensation or batch condensation. So instead of starting with the liquid and then vaporizing, you could start with the vapor and then condense it. Okay, and you are just inverting the process. You start with the vapor, bring it to the dew point, collect the first drop of liquid, and then cool further, collect the other drop of liquid, and then you continue this, and then you will be having a composite condensate. Okay, and you can do the same side of operation in the reverse case also. So we call that as a partial differential condensation. Yeah, differential condensation. So here a vapor mixture is condensed to create an infinitesimal amount of liquid and swiftly removed. Okay, and then you do this over and over, and then you'll get a vapor which is always at dew point temperature, but the liquid condensate that you create would have an average composition. Okay, so in this case you can again write F times YF should be equal to D times YD plus W times some X average. Okay, so at the end of the partial differential condensation, the total moles that you had should be distributed between the vapor and the liquid. Okay, and the liquid will have an average composition because here the liquid compositions keep changing at every cut that you get. So you can write the same kind of a mass balance we did before. I will show you the equations and final result, and you can check this later on. So here we'll do the mole balance, moles in, moles out, accumulation, and then total material and species A. So moles in 0 for both, moles out is DL, and here this would be XDL. Accumulation is DD, and here you have D of dy, which is nothing but ddy plus ydd. So you can see that here what I have written is that the moment the first drop of liquid is formed, that would have x times dl amount of A that is out of the system, that is gone. Okay. Now the vapor would have undergone change in the composition as well as in the total moles. That's why I am writing d of dy. So now we can write the mass balance for total material. So in is 0, out is dl, and that is equal to the accumulation. So dl equal to minus dd. And for species A, in is 0, out is xdl, and accumulation is ddy plus ydd. And this dl can be written in terms of dd, so I will have x dd is equal to ddy plus ydd. So you can see that you have a similar set of equations like before for batch distillation. So the only thing here is this x minus y is again something which has to be obtained from Rayleigh data. You can assume constant relative volatility, and you can do the same thing that we did for Rayleigh's equation. So I will give you the final expression. You can cross check this. Okay, let's just quickly go back and see what we have done so far. So I was talking about batch distillation or simple distillation or differential distillation. They all mean the same. Effectively, this is very similar to flash operation, except that flash operation happens in single stage. You bring the vapor or liquid to the two-phase region and let it equilibrate and phase separate it. It's a single stage operation that gives you one shot opportunity to separate the mixtures. But this is very simple, okay. But now if you can change the setup such a way that the moment the vapor is formed, if you are able to separate it out from the system, more and more vapor can form continuously, okay. And then you can collect this continuous production of vapor together, and then you can collect it. So this we call it as a differential distillation or batch distillation. From the operation point of view, like I said here, you start from a liquid, reach the bubble point, create the first vapor, remove it, okay, and then you supply more heat, and then you travel along this bubble point, okay. At each point when the vapor is created, you are separating it out, okay. So this basically means doing a very large number of or infinitely large number of flash operations at each of these points, okay. And we looked at this apparatus. The apparatus is very simple. You start with a kind of a reboiler or a vessel where the liquid is charged, and then you have a heating mechanism. You basically supply heat constantly, okay. And you can see that if you look at this curve, you start here and then you move up here. That means the temperature of the kettle will keep on increasing as you continue, because you are going to lower and lower composition of X, meaning you are reaching close to TB. So if you were to put a thermometer here as the batch distillation happens, you will see the temperature keeps increasing, okay. And the vapor, as it is formed, the vapor is taken away to the condenser, and then you can collect it to the liquid. So this is from an operation point of view, and we can set up a very simple mass balance or mole balance approach, and then you can relate the quantities that are involved, okay. So for example, we establish this Rayleigh's equation that tells the relationship between the amount of liquid left over after the operation to the initial feed and then to the composition of the initial and the final liquids. And then it also involves VLE data, and then we said that we can get an analytical expression if I can relate y as a function of x using a constant relative volatility, and that basically yields us this kind of set of equations. So you don't need to do graphically, you don't need to do numerically. This equation is very simple enough to use. Typically most of the things will be given and one of the things will be unknown. That's what you have to find out. Okay. And the opposite operation of differential condensation means that you start with the vapor and then you cool it to the dew point, create the first liquid droplet and separate it out. Okay, cool further, another new droplet of liquid will form, separate it, and then you keep doing this over and over. Okay, you are collecting very large number of this condensation process, and equivalently you can write a set of mass balance, and then you can, the approach is very same. Okay, you're going to write x as a function of y here. There we wrote y as a function of x. Here the variable is y. So you replace x in terms of y using constant relative volatility, and then continue this integral, and then you'll get a final expression. Okay. So distillation, there are three things. Okay, there are three kinds of distillation: flash distillation, differential distillation, and there is something called continuous fractionator. Okay, so that is a broader design problem. Before we do that, I will do some problems in the next class, and then Thursday you will have some problems to solve in the tutorial session, and then next week I will talk about the binary continuous fractionators. Okay, so that's all for today.